Hello, for this video I'm gonna talk about these exercises regarding Faraday's law. So here we have calculate ampere turns. When we talk ampere turns, we are talking about MMF, magnetic force, and this is equals to the number of turns times the current. In this example, we have 100 turns times a current of 4 milliamps. That is the same that 10 to the minus 3. And this just gives us a 6 amps ampere turns of MMF. Now we have find the fuel intensity of 40 turns, 10 centimeter long coil. So fuel intensity H is equals to number of turns times the current over the mean length path that the flux is going through. So for this case we have an N of 40 turns. We have 3 amps over a mean length path of 10 centimeters, because that's the coil. So 10 to the minus 2, because we have to move it to meters, and that's because the fuel intensity is given in ampere turns. Sorry about this. Turns over meters. Okay. Now B, if the same coil is stretched 20 centimeters. So here we can see the drawings actually. So in case A we have 10 centimeters, and in case B we have 20. So it's the same, just that the mean path changes. So H is still 40 times 3 number of turns amps, but in this case it's 20 centimeters, and give us a 600 ampere turns over meters. Now for the part C, it is telling us that if we have number 10 number A number A, the same coil of in A, but we put an iron core of 20 centimeters, what will be the fuel intensity? So this is actually the same case that have in B, because here the path of the flux will be the same of the iron core. All of the flux will be traveling through the core, so we have the same 20 centimeters and not the 10. So the answer will be the same than this one, 600. Now for part 3, a coil has an MMF of 500 ampere turns and a reluctance of 2 times 10 to the power of 6. So for this one we need to get the flux, 5, and flux is given by the formula MMF over reluctance. In this case the MMF is given 500 ampere turns, and the reluctance is given as well, 2 to the power 2 to the 6, and this is 2.5 times 10 to the minus 4 Weber. and that's it. The formulas are pretty easy for the flux, for the fuel intensity, and MMF. Okay, now we have this exercise in part 8. They are telling us to find MMF. So, as we said before, MMF is equals to the number of turns times the current. And in this case, for part A, we have that the number of turns is 8 and the current is 5 amps. So we have 40 ampere turns of MMF. And they want us to find the fuel intensity too. So as we talked before, this is MMF over the mean length path. In this case, MMF is already calculated, 40 over the mean length path that is given to, that is a 5 centimeter long. So 5 times 10 to the minus 2 because we have to given in meters. Because as we talked before, the fuel intensity is given in ampere turns over meter. And now for part B, they say that an iron core is put in the coil, in between the coil, in the middle of the coil. So as we can see here in the formulas, the permeability mu does not affect the MMF or H. So the values will not change. MMF will still be 40 ampere turns and H will be still 400 ampere turns per meter. That's it. Now for the next exercise, we are gonna actually work with a core and a coil. So for this one, they are asking us to draw the magnetic circuit and assume a permeability of mu r, okay? And they want us to figure out the flux and the inductance, okay? Now for the next exercise, we are gonna actually work with a core and a coil. So for this one, they are asking us to draw the magnetic circuit and assume a permeability of mu r, okay? And they want us to figure out the flux and the inductance, okay? So first we need to consider the magnetic circuit. The magnetic circuit, we can think of MMF as an analogy of the power supply. So we have MMF, that's MI. This will be our power supply. We are given that we have 200 turns and we have 1 ampere of current. So if we multiply that, we have a 200 ampere turns. So we know that our supply will be 200 ampere turns. This is our force that is gonna drive the circuit. Now we have the reluctances. When we talk about reluctance, we have the equation of reluctance is equals to the length of the mean path, the reluctance of the air times the reluctance of the core times the area, the cross-sectional area. Okay, so here when we see this core, we could divided into 4 reluctances. One that goes this way, another that goes from the top, another that goes from the right, and another that goes from the bottom. And we can see that the path from these three, the one that goes to the left and top and bottom, is the same path. The flux will travel the same mean path. But since this distance is different than the 15 here, then there will have a different reluctance here. So to calculate the reluctances, we will divide it like that. And also that's how we are gonna draw the magnetic circuit. You're gonna have one reluctance to the left, one in the top, one in the right, and one in the bottom. So I'm just gonna call it R1, R2, R3, and R4. And as I thought before, R1 is equals to R2 and equals to R4. They're gonna be the same. Okay, so let's calculate R1. R1 is gonna be equals to, remember we are talking about the mean length path. So when we talk about the mean, we are gonna talk about the reluctance going through, let's say, the middle. So when it goes from here, it doesn't go from 0 it will not travel this whole path. It will travel half of this, and all of this. So we have half of 15 plus, it will go from half of 15, then it will travel all the 30 centimeters, and again another half of 15. So it will go from here all this way, and then half, and then it will turn here. Remember, we're doing this is because we're talking about the mean path, what is the average that it will travel. Then we divide this by mu naught. Mu naught is the reluctance, the permeability, of the air, and is given here for pi times 10 to the minus 7. So we have 4 times pi times 10 to the minus 7 times the reluctance of the core, the permeability of the core, again, that is 2500, times the cross-sectional area. So here we have 15 on one side, and it is telling us that it is going 10 centimeters into the page. So the cross-sectional area will be 15 times 10. And now this is in centimeters, so the top part we have to multiply times 10 to the minus 2, because we need this length in centimeters, and this will be in centimeters squared, so we have to multiply to 10 to the minus 4. And this is going to give us a reluctance of approximately 5, 9, have done it before, so I just have it here, of 9,549, and the units for reluctance is ampere turns over Weber. Sorry, Weber is just WB. So this is the reluctance for this side, and if we think about it, R1, R2, R4 are equals, because when the flux travels, it will go from half 15, it will go 30, and again half 15 here. So number 3, R3, we have at the beginning that is kind of the same. We have that it will travel from half 15, 30 and half 15. So I'm just gonna write 45, that is what we have here, times 10 to the minus 2. The permeability of air is gonna be the same. The permeability of the core is the same, but this time instead of 15 here, the distance here is just 10. So the cross-sectional area is gonna be 10 times 10 because it is going 10 centimeters into the page. So we have 10 times 10 times 10 to the minus 4 because we need it in meters. And this is gonna give us a reluctance of I have it right here, approximately 14,000 amperes over Weber. Okay, so we have R1 and R3. So now we need to calculate the flux, that is the actual question that is given us, and we have the flux is equals to MMF over the reluctance. It's like an analogy for current. Current equals to voltage over resistance is like the analogy that is mostly done. Flux being current, MMF voltage, and reluctance resistance. So we already calculated MMF, that we said that it was 200 ampere turns. 200 ampere turns. And we now have the reluctances that are gonna be R1 plus R2 plus R3 plus R4. So we have 200 ampere turns. We have the reluctance of R1, that is this. And we multiply it by 3 because these 3 are equals, plus the reluctance of the one that was different, and this is gonna give us a flux of 4.65 times 10 to the minus 3 Weber. Okay, so that's how we calculate the flux when we are given the reluctances and the MMF. Now, it is asking us about the inductance of the coil. So, for the inductance of the coil, we need to consider that we can calculate the flux linkage by multiplying the inductance times the current. So this is the flux linking the coil. This is n number of turns. So if we want inductance, we can have it as the flux linkage over the current. Now this is the current produced by the flux. So we have a 200 turns, a flux that we just calculated, and we divide this by the current that is given to us, that is 1 amp. And when we calculate this, it's just gonna be 0.96 Henry. So this is how we calculate the inductance when we are given the flux leakage and the current. So what you can take from this video is that the use of the formulas and the terminology. Ampere turns is just MMF, field intensity is H, and the flux. Also, it's important to remember the analogy of MMF being the voltage, reluctance the resistance, and flux the current. That will help you to build the magnetic circuit. And that is it. Okay, now we are going to tackle an exercise with when we have air gap. So the first thing they're asking us, and the first thing that we should do is draw the magnetic circuit. So we just have one coil, so this will be our MMF, and they are all giving us already one mean path of 12 centimeters square. Well, this is the cross-sectional area, I'm sorry. 14 centimeters is the mean path, so we can consider all of this just one reluctance with this path. And then we have another reluctance that is gonna be the cross-sectional, the air gap. So here we have another reluctance that is, so I'm just gonna call this RC for reluctance of the core and RG for the reluctance of the air gap. So as we just saw, reluctance is the mean path over the permeabilities of the core and the air times the cross-sectional area. So to calculate the reluctance of the core, we just need the path, that in this case is 40 centimeters. We multiply by 10 minus 2 to make it meters. And we have the reluctance of air, that is 4 pi times 10 to the minus 7. And now we need the reluctance of the core. Let's see if it is given. Yes, it is given, and it says that it's 4,000. No reluctance, permeability. I always confuse the terms. And now we need the cross-sectional area. So we have 12 centimeters square, and we multiply this by 10 to the minus 4 to make it meters, and that gives us a reluctance of the core of approximately 66,000 ampere per turns over Weber. Now we do the same for the reluctance of the air gap. And now the length path in this case is just 0.05 centimeters. That is the mean path that the flux travels through the air. So 0.4 centimeters, we change it to meters, and then we multiply by the reluctance, the permeability of the air. And in this case we don't have mu r, because mu r is regarding the core, and because we have air we only have the permeability of air. And we multiply this by 12, that is the cross-sectional area, 12 centimeters square. But here we need to be careful, because it is telling us that the air gap increases the effective cross-sectional area by 5%. So when it says this, it means that the the flux travels a little bit away from the cord. It doesn't go exactly across like this. It has a little curve. So that is that 5% that is talking here about. So the total area changes. So here we have 12, but this 12 we need to increase it by 5%. So it will be 1 times 1 plus 0.5. And we multiply this to 10 to the minus 4 because this will be centimeter squares and we need meters. So here we are just adding that 5% to the 12 centimeters square of the cross-sectional area. And this is going to give us a total flux, reluctance, sorry, of approx 315,000 ampere turns over Weber. Okay. Now that we have the two reluctances, we can calculate the total reluctance, that is just the sum of both of them, because if we look at the magnetic circuit, we can see that they are in series, and this will give us a total of, if we just add them up, this is approximately 382,000 ampere turns over Weber. Okay, and now we have done the first part, that is what is the total reluctance, and they want to calculate the current required to produce a flux density of 0.5 Teslas. So now we need to talk about flux density. Flux density is given by P. So let me write it a little better. Is B. Now B can be seen a formula for flux, that is B times the area. So if we want to calculate the flux with a given value of flux intensity, we just use this formula. In this case they are telling us that is 0.5 Tesla, and we multiply this by the cross-sectional area, and in this case they are talking about produce in the air gap, so we use the same area that we work for the reluctance of the air gap, so it will be 12 times 1.05, because we need to account for that 5% fringing, 10 times to the minus 4, because we need this in meters. So this flux will be 6.3 times to the minus 4 Weber. And now that we have the flux, we can calculate the current. Another formula for flux is just MMF, that is Ni, times the reluctance. So if we want the current, we just need to multiply the flux times the reluctance and divide it by the number of turns. Now, because we have a series circuit, we need to take into account both reluctances, so the total reluctance. to calculate this current. So we have 6.3 times 10 to the minus 4, that is our flux. We multiply it by our total reluctance. I'm just gonna write RT because it's a big number. I don't feel like writing it again. And we have 400 turns. So if we calculate all of this, we are given a current of 0.6 amperes. Okay, and that's how we can calculate the total reluctance, and when we have a air gap, how we can get the flux in the air gap and the current. Now for the last exercise, we're going to talk about the electromotive force. This comes still from Faraday's law. We have the transformer action, and this can be taken as a time-varying field induces a voltage in a coil linking the field. So that sounds so complicated, but basically we have this force, the EMF, is equals to the number of turns times the change in time of the flux. So here they are asking us to calculate the voltage. There will be the EMF, when we have this sinusoidal form. So this is pretty simple once we have the formula, because we have the EMF, but they want us to write it as voltage, so let's say voltage. It's going to be equals to the number of turns, in this case 100, times the derivative of the flux, and the flux they are giving us to 0.05 sine of 370, and this is con respect to time, in respect of time. So here we can take out this 0.05 out because it's a constant, and multiply it by 100. So we will have 5. And when we derive a sine, or well, here we're just gonna use the product rule, and we would derive the inside, and then we derive the outside. So we will have times the inside will be the derivative of this, that is just 377, times the derivative of the outside, that it will be cos. Derivative of sine is just cosine. So, and we can say that the voltage will be this 1885 cos of 377 t. So if we have the flux, it's pretty easy to calculate the EMF, that is the voltage. And they are talking about the polarity. So in this case, the polarity doesn't really matter because we have a cosine. So if we were to plot this, we will have something like this. I'm sorry about my drawing. So we will have plus and a minus, so the polarity will be changing. So this is AC, so there is no polarity. And that is it. I hope this video helps you to study for your exams.